Okay, so here we're going to do an example. We have a metal sphere of radius a and it carries a charge q. The sphere is surrounded out of some radius b by a linear dielectric of permittivity epsilon. And what we want to do is find the potential at the center. And we do this relative to infinity. Now, to determine the potential, we need to know what the electric field is. And to find the electric field, we will first need to calculate the electric displacement. Since the setup is spherically symmetric and we know what the free charge is, which is Q, what we can do is we can write out our equation for the electric displacement, which is the surface integral. So the integral of d dot dA should be equal to the total free charge enclosed. Free charge enclosed. Okay. So now what we have for d then, this should be equal to 1 over 4 pi r squared q times r hat. Okay. Now this is for r greater than a. Now inside, what we know is the electric field is going to be 0. So to have a 0 electric field, this is going to be equal to the polarization, which is equal to the electric displacement, and all of this is going to equal 0. So now what we're going to do is we're going to make use of the fact that the electric displacement is equal to epsilon times the electric field. Okay, so what this means is we can now determine what our electric field is, and we're going to do it in two regions. So first of all, we're going to write out the electric field for the region between A and B. Okay, and what this is going to be given by is 1 over 4 pi epsilon by r squared. I'm going to put the q on the top. So we have q and we have r hat. Okay, so here we can see that the electric field in the region between A and B depends on the permittivity of the material. The other region I have to consider now is for R is greater than B. Okay, so this is away from the surface. And for this, what we have is the electric field will be equal to Q divided by 4 pi epsilon naught times R squared. It's in the R hat direction. Okay, now all we want to do is determine the potential. So to determine the potential, we just have to do the line integral. So we have the potential will equal the minus the integral from infinity to 0 of E dot dl. Okay, so we're going to work our way inwards. So first of all, we're going to integrate from infinity to the surface of the dielectric. So we have minus the integral from infinity to b. Now the electric field that we found in this region was given by Q divided by 4 pi epsilon naught r squared dr minus the next region we look at is between A and B. So we have the integral, we're going from B into A, so it's B A. Our electric field is given by Q divided by 4 pi epsilon r squared dr, and the final region is that inside, which was going from A into the center, which is 0, so that'd be minus the integral from A to 0. The electric field in this region is equal to 0, dr. Okay, so now what we're just going to do is just going to write this out a little bit neater and solve it. So what we find then is that our potential would be equal to Q divided by 4 pi into 1 over epsilon naught by B plus 1 over epsilon by A minus 1 over epsilon by B. So in the next part, we're going to determine what the surface charge is. We're going to look at the polarization.